In this lesson, we will look at the combustion process in a piston engine, and then we will go on to examine the problems of detonation and pre-ignition, both of which can occur during the combustion phase. Combustion of the air and gasoline mixture in a piston engine is the controlled rate of burning. It is not an explosion. The mixture induced into the cylinders consists of gasoline vapour, 84.2% carbon and 15.8% hydrogen by weight, and air, 78% nitrogen, 21% oxygen and 1% other inert gases. When combustion has been completed, the hydrogen in the fuel will have combined with the oxygen in the air to produce H2O in the form of water vapour. And the carbon in the fuel will combine with the oxygen in the air to form carbon dioxide, or CO2. The nitrogen and other gases play no active part in the combustion process, but they do form the bulk of the gas that is heated and expanded to create pressure energy. The nitrogen also slows down the rate of combustion. Without nitrogen, combustion would be an explosion with far too rapid a temperature and pressure rise to allow it to be harnessed to do useful work. When normal combustion takes place, the compressed mixture in the cylinder is ignited by the spark and burns steadily with a flame front velocity or flame rate of 60 to 80 feet per second, giving a steady and smooth temperature and pressure rise in the combustion chamber. Maximum pressure will be generated when combustion has been completed, and ideally this should occur when the crank is at 8 to 10 degrees after top dead centre, TDC, where, because of the ineffective crank angle, the volume of the combustion chamber is still at a minimum. Should maximum pressure conditions arise in advance of this, that is at or before crankshaft reaches top dead centre, the engine would tend to run backwards. As combustion takes a period of time, albeit a short one, in order for combustion to be completed when the piston is 8 to 10 degrees after top dead centre, the spark must occur before the piston reaches top dead centre. The flame rate remains reasonably constant, so if the ignition point remains the same, the point in the cycle where combustion is completed will vary with variations in engine speed. At low engine speeds, it is necessary to initiate ignition later in the cycle to prevent the maximum pressure building up before the piston reaches top dead centre. The term used for this is retarding the ignition timing. As the engine speed increases, it is necessary to initiate ignition earlier in the cycle so that the maximum pressure still occurs at 8 to 10 degrees after top dead centre. This is known as advancing the ignition timing. The flame rate can vary slightly. The mixture will burn faster if it's made richer, that is to say, the proportion of fuel in the mixture is increased. This is because the proportion of nitrogen will be reduced. The mixture will also burn faster if the pressure in the cylinders increases. An instance of both these events occurs on takeoff, when it's necessary to richen the mixture strength in order to ensure stable combustion because the engine is producing high power. This at least partly offsets the requirement to advance the ignition timing at high engine speed. Because single-engine light aircraft have a greater need for reliability than for efficiency, the ignition timing is usually fixed at an intermediate position and not adjusted. As we have said, during normal combustion, the flame travels smoothly and steadily through the mixture as the advancing flame front heats the gases immediately ahead of it, so that they in turn burn. Detonation, if it occurs, happens after ignition and is unstable combustion. Detonation happens because progressively more and more heat is concentrated in the flame front, which is brought to bear on the remaining unburnt portion of the mixture, termed end gas, and its temperature is raised. In addition, the burnt gases have expanded, so the end gas is subjected to an increasing pressure and therefore its temperature increases further. If there is sufficient pressure and heat available to bring all the end gas to the point of combustion at the same instant, it will explode or detonate. The flame rate will increase to 1,000 feet per second, with a degree of violence which will depend on the amount of end gas that remains. The explosion of the end gas can cause the piston crown to burn and eventually to collapse. This picture shows a piston which has been severely damaged by detonation. The piston crown has been burnt and eventually it has disintegrated. Overheating of the combustion chamber can also occur. This may cause the valves to split and distort. It might also damage the spark plug electrodes. The damage shown here is consistent with being caused by detonation. There is also a sudden rise in pressure as detonation occurs, which applies a shock loading to the engine component parts which may cause mechanical damage, particularly to the big end bearings, and even the connecting rod, although the case shown here is extreme. Finally, because the maximum pressure is generated before the piston is in the correct position to utilize it, the piston has to overcome a high back pressure and power is lost. There are a number of reasons why the temperature in the combustion chamber can become excessive, causing detonation to occur. Any of the following, either individually or in combination, can give rise to the onset of detonation. Any condition that heats the charge before combustion will increase the temperature of the end gas. Preheating the air before it enters the engine by the use of carburetor heat to overcome carburetor icing, for instance, or overcompression in the supercharger or turbocharger may well give rise to excessive charge temperatures. The weaker the mixture selected, the hotter will be the temperature of combustion. Conversely, if the mixture is made richer, it will burn cooler and more quickly, thus combating detonation. The formation of carbon, or coke as it is sometimes known, in the cylinder head will prevent heat dissipation, possibly bringing the temperature of combustion up to the point of detonation. Advancing the ignition timing, in other words igniting the mixture too early, may cause cylinder pressures and temperatures to rise too rapidly, possibly causing detonation to occur. If a fuel with an octane rating lower than that which is recommended is used, it will promote detonation, especially under high power conditions. It's important, therefore, that fuel of the recommended octane rating is used. If this fuel is not available, then one with a higher octane rating may be used. The fact that detonation is occurring can be recognized by a metallic knocking sound, sometimes called pinging, which is caused by the violent vibrating pressure waves striking the walls of the combustion chamber. A great deal of damage may be done under high power conditions, particularly in an aircraft where, because of the noise created by the propeller, the detonation may go unnoticed until it is too late. Engine designers can help to prevent detonation by ensuring that the flame is started from the vicinity of some hot spots such as the exhaust valve, so that the end gas is pushed away from the hotter parts of the combustion chamber and compressed into a cooler part. In order to reduce the time taken for the flame front to travel across the combustion chamber and therefore the risk of detonation, some engines are designed with two spark plugs which initiate the flame simultaneously from two different points in the chamber. pilot can also take a number of actions to help prevent detonation. On aircraft with variable pitch propellers, the same power may be obtained at a higher engine speed by using a finer propeller pitch. This enables a smaller throttle opening to be used, which helps in two ways. The smaller throttle opening reduces the cylinder pressure, and the higher running speed cuts down the time available for detonation to develop. Carburetor heat should not be used at very high engine power settings, such as during takeoff. A rich mixture should be used at high power settings. Pre-ignition is the ignition of the charge before the spark occurs at the sparking plug. This is usually caused by a local hotspot in the combustion chamber, such as incandescent carbon or very hot sparking plug points. Pre-ignition can cause the engine to run very erratically. If, as in a car, the ignition switch is used to shut down the engine, it may continue turning over if it is still supplied with fuel. This is called running on. The engine performance will suffer greatly because the ignition is effectively retarded. This in turn will cause the engine to overheat, which exacerbates the situation.